Inspector, I would like to practice my presentation of Welding Summit. I'm here in the Woodlands, Texas. There's just a few hours, a couple of hours maybe to present. So I would like to practice. My presentation going to be about corrosion in welding joints. So corrosion can be defined as the deterioration of the substrate. Corrosion is a natural process that shows the tendency of materials to give up energy and return to their natural state. Perhaps we already know that, but the question now here is, how does it affect joints in steel structures? It is important for us to understand that corrosion is a process that cannot be completely stopped. We generally aim to delay, to counteract it, and design against this phenomena, but eventually, under suitable conditions, this process will occur. The most widely used method for preventing corrosion nowadays, specifically in carbon steel, is the application of high-performance protective coatings. These kind of coatings protect thousands of structures and other kind of metal products around the world. Well, in summary, in a nutshell, the corrosion process starts when we can bring together 5 elements. These are cathodic zones, anodic zones, metallic fats, oxygen, and electrolyte. Typically, in metals like steels, we implicitly find the first 3 elements, the metallic path, the anodic, and the cathodic zones. Oxygen is naturally present in the atmosphere in some form or another, leaving us with the electrolyte as the remaining element. So this electrolyte is commonly found in the environment where our system is located, often in the form of humidity. We typically strive to prevent this electrolyte from encountering our material through coatings. And that's how typically corrosion cell is formed. In the welding world, corrosion refers to the gradual deterioration or degradation of metals and materials due to chemical or mostly to electrochemical reactions with their environment. Corrosion can occur in several forms, and it is a significant concern for weld structures and components. When metals are joined through welding, they may become more susceptible to corrosion, especially in the areas near the welds. Welding can introduce microstructural changes and residual stresses in the welded region, altering the material's corrosion resistance. Additionally, the welding process can create those areas with different metallurgical characteristics, leading to the formation of galvanic couples and promoting galvanic corrosion. The introduction of, for example, weld effects, such as, porosity or inclusions, or maybe undercuts, can act as localized sites for corrosion initiation, leading to heating corrosion. Several factors influence the rate and severity of corrosion in welded structures, including the type of metal used, the welding processes, the environmental conditions, and the presence of contaminants. And proper welding techniques, appropriate material selection, and the use of corrosion-resistant coatings or treatments are essentially to mitigate corrosion in weld components and ensure, of course, the long-term integrity and reliability. Regular inspections, maintenance, and protective measures are also crucial to manage and prevent corrosion-related issues in the welding industry. So there are various causes of corrosion in materials, and much of it depends, of course, on their interaction with the environment and their performance within the containing system. One thing to keep in mind is that welding can be a critical area of our assets. Therefore, specific degradation in the area can have undesirable consequences and can occur more rapidly compared to other areas of the component in question. So let's delve into some, and it is important to emphasize only some, because there's a lot of the corrosion mechanisms that can be found in welded joints. More precisely focus on carbon steel joints welded through conventional electric arc processes. There are a few. They are the most common corrosion mechanisms of welds. We have, for example, galvanic corrosion. This is due to joining of different metals. Pitting corrosion, mostly in areas affected by microstructural heterogeneities. Stress corrosion cracking, due to residual stresses from welding. Intergranular corrosion in susceptible alloys. So the corrosion process depends on various factors. There are several factors, and the characteristics of corrosive processes in a weld are influenced by several aspects. For example, the first one, differences in electrochemical potential. So different electrochemical potentials can lead to a galvanic corrosion where the similar materials are in contact or part of the same circuit, same electric circuit. The presence of corrosive microenvironments. The second one, okay, the environment in which welds are situated can significantly affect the corrosion process. The impact of corrosion will not be the same for a structural weld located in a low humidity area, for example, Arizona, compared to a weld applied to a process pipe near the coast, which also has poorly applied maybe insulation, leading to phenomena like corrosion under insulation or PUI. In corrosion under insulation, the insulation can sometimes retain the necessary electrolyte, and since an increase in temperature accelerates chemical or electrochemical processes like corrosion, this can result in corrosive implications. The next one, for example, means the inclusion of impurities in the weld, whether due to material quality issues, design errors or mistakes, or atmospheric conditions during the process, can promote certain types of corrosion. Certain elements might reduce corrosion resistance by inhibiting passivation, like, for example, chromium in stainless steel. This is why certain cleaning materials or testing materials, solvents, for example, like the use during a testing that is called dipentra testing, with high halogen or chlorine content are not recommended. On the other hand, impurities might alter salinity levels or ion concentrations, creating areas with higher electric activity potential and, of course, leading to corrosion. All these factors must be considered in a comprehensive corrosion protection scheme, which might involve coatings, for instance. About the alteration of the crystal structure, regarding this point, heat plays a significant role, and certain treatments can result in effects such as precipitation of chromium, stainless steel. So I have some examples about corrosion, of course, with pictures. The first one is the uniform corrosion. This is a form of corrosion in which a metal is attacked at the same rate across the whole surface, the entire surface. The areas of anodes and cathodes on a corroding piece of metal typically change over time. So that areas that were once anodic become cathodic then, and vice versa. If the depth of attack at any point exceeds twice the average of depth of attack, corrosion is not longer considered to be uniform. This is another one. I took this photo during an inspection project in Mexico, in which I was working a few months ago. Of course, there's a mechanical damage. This is a flange. This is a welded flange. And of course, there is a mechanical damage here and here, okay, the weld. It was caused by personnel while attempting to install the bolts. It didn't fit. They make this grind to make them fit. So, of course, both this damage and the type of material of the bolts used have initiated this corrosion process. This mechanism occurs when two different metals are in electrical contact, exposed to electrolytes such as water or humidity. And the combination of metals creates a galvanic cell where one acts as an anode and corrodes preferentially, while the other acts as a cathode and undergoes slower corrosion. The presence of different electrochemical potentials between the metals drives the flow of current and accelerates corrosion. Galvanic corrosion can significantly affect the structural welding joint, especially when the similar metals are in contact or are part of the joint. This is a galvanic series. This is a very helpful tool which lists the materials from the active ones to the noble ones, the less active ones, the passive ones, okay? In the welding context, this can happen when, for example, carbon steel and stainless steel are joined together, or when the steel is connected to aluminum, copper, so on. So when galvanic couple is formed in a welding joint, one metal acts as the anode and corrodes faster, while the other metal acts as the cathode and corrodes at a slower rate. And this can lead to several issues. For example, the first one, accelerated corrosion, when the anodic metal, the less noble metal, we saw in this galvanic series, corrodes more rapidly than it would if it were not in electrical contact with the cathodic metal. Okay, so this can lead to localized and rapid degradation of anodic metal, potentially weakening the joint. The second one is corrosion at the interface. What the weld zone itself can act as microgalvanic cell due to variation in the composition and microstructure, leading to corrosion at the interface between the metals. The third one is formation of crevices. The presence of the similar metals in the joint can create crevices and gaps where the corrosion can occur, and can occur more aggressively. These crevices can be challenging to access and protect, making them susceptible to accelerated corrosion. So to mitigate galvanic corrosion in structural welding joints, several measures can be taken. For example, the use of compatible metals whenever possible, use similar materials in the joint to minimize the potential of galvanic corrosion. The isolation technique is employ isolation methods such as coatings, insulation materials, or gaskets, for example, to physically separate similar metals to prevent direct electrical contact. And of course, perhaps my favorite is proper coatings or proper treatments. Apply appropriate corrosion-resistant coatings and treatments to the joint to provide an additional barrier against corrosive environments. And by understanding and addressing galvanic corrosion, engineers and welders can ensure the long-term integrity and reliability of structural welding joints, reducing, of course, the risk of premature failure and enhancing an overall performance of welded joint or welded structures. This is pitting corrosion. It occurs when small cavities or pits form on the material surface due to the presence of microscopic defects or imperfections, such as, for example, inclusions of particles or contaminants in the weld. And these pits act as focal points for localized corrosion and can penetrate deep into the material. Pitting corrosion, it is important to note that pitting corrosion is a form of localized corrosion where small pits or cavities form on the surface of the metal. It can occur when certain areas of the metal surface become more susceptible to corrosion due to various factors, such as impurities, inclusions or microstructural variations can have a significant impact on the structural welding joint, leading, of course, to localized and often severe damage. So here's how pitting corrosion will affect structural welding joint. The first one is localized weak points. Pitting corrosion creates those small holes or pits in the metal surface, and these pits act as localized weak points, reducing the material's load-bearing capacity and compromising the joint's structural integrity. The second one is stress concentration. The presence of pits, it is important to know that, can lead to stress concentration points on the metal surface. When the joint is subjected to mechanical or applied loads, the stress around the pits can be significantly higher, making the area more susceptible to crack, initiation, and propagation. Then we have the rapid penetration. Pitting corrosion can penetrate deeply into the metal, often at a much faster rate than any for corrosion. So this rapid penetration can result in the sudden failure of the joint, especially if the pit growth is not detected and addressed at time. Difficult detection, of course, is a concern because pits are small and may not be readily visible during routine inspections, even using ultrasonic testing, conventional ultrasonic testing systems. As a result, pitting corrosion can go unnoticed until it has caused significant damage or failure. We have another effect, like, for example, galvanic effects. Pits can act as local galvanic cells, with the pit acting as the anode and the surrounding metal as the cathode. This can accelerate the corrosion process, leading to further degradation around the pits. So to mitigate the impact of pitting corrosion in a structural welding joint, several measures can be taken. For example, the material selection. It's important to choose materials with good corrosion resistance, especially in environments where pitting is likely to occur. Surface finishing. It's important to employ appropriate surface finishing techniques to minimize the presence of surface defects and impurities that can act as creation sites for pits. And of course, protective coatings, apply corrosion resistance coatings or paint systems to provide an additional barrier against the corrosive environment. This is another type of corrosion in welds, very common corrosion system. That is concentration cell corrosion, crevice corrosion. Corrosion by concentration cell is often referred to as crevice corrosion because the environmental differences that lead to this type of corrosion are often localized or in crevices. Those crevices could be metal to metal, metal to non-metal contacts. And the most prevalent form of concentration cell corrosion occurs with varying concentration of oxygen. Accelerated corrosion takes place in this scenario. Three most common examples of crevice metals components are intermittent welds, back-to-back angles, and areas beneath both heads, too. And of course, welding discontinuities and undercuts, lack of fusion, porosity, and so on. So crevice corrosion is a type of corrosive attack that occurs within confined space or crevices that form when components are in close contact. There are often, and this is an important point that I would like to share with you, that I call the importance of mixing inspections, inspector versus inspector. So there often exists bias among inspectors or engineers in different areas. One that I see quite frequently is the debate between welding specialists and coating specialists. In this scenario, both parties are often unaware of the process undertaken by their counterparts. In the absence of effective prefabrication meeting, they start having discussions about the optimal condition of a weld profile should have before applying coating system. And this leads to problems. On one hand, the welding team seeks to defend their perspective while ensuring structural integrity. And on the other hand, the coating team seeks an optimal surface condition for the effective performance of the adaptive coating system. I figured out that communication and understanding from both sides are crucial for resolving this type of situations. And there are two standards that govern this reconciliation process between welding inspection and coating inspection. The first one, and perhaps my favorite one, is the NACE SP178. This is a great tool which allows inspectors to upgrade an optimal surface condition between welding and coating processes and provide this type of plastic replica that is very useful to agree which type of surface condition going to be accepted and going to be rejected before the process. So this is a very important tool during our prefabrication meeting. There's another one, the ISO 8501 Part 3. This is called preparation of steel substrates before application of paints and related products. It's a visual assessment of surface cleanliness. The Part 3 means preparation grades of welds, edges, and other areas with surface imperfections. So both of them are very useful. Field inspection designed to agree during a project which type of welding discontinuities or welding conditions going to affect the coating process and, of course, the coating system performance. There's another fact. As you can see here in this picture, we have this coated pipe with not a lot of damage here in the base material zone on both sides, but very important damage here, the welded zone. An important point here is that, as we know, temperature changes can lead to different hardness levels in both the weld and the heat-affected zone. This might not pose an issue for mechanical integrity of the component, but it does affect surface preparation. You might be familiar with this term sandblast, which is just one of all of the processes used in the coatings to provide cleanliness and roughness of the surface of the material to be coated. So this process might not perform well if this phenomenon of hardness changes in the surface exists. Additionally, we must consider the surface tension effect of the paints. This part, okay, which through adhesive and cohesive forces can reduce the thickness and edge at edges, corners, welded joints. So we have this situation where the weld zone and the heat-affected zone are generally less protected by conventional application methods. To address this, we have this process called stripe coat. This is which involves applying an additional coat either before or after, usually before, the main coating layer. And this can be found in this document, SSPC Guide 11. This guide discusses the technique called stripe or coat stripping as a way of providing extra corrosion protection measures, edges, outside corners, crevices, bulkheads, of course, welds, and other irregular steel geometries, including optional technique that can be used to improve coating performance, like this picture. And another topic of interest, at least to me, is how certain inspection methods, specifically non-destructive testing, can potentially lead to corrosion damage in welds. This is an example. This is a dye penetrant testing in a boat, in a ship, in a large ship, a tanker ship, doing a repair. And this is an example of a poorly executed liquid penetrant testing. We must understand that part of the process involves post-cleaning of the test area. And this also applies to tests like ultrasonic, because the ultrasonic testing code plan sometimes is not the best material. Sometimes it's not keeping in mind that could lead to corrosion process. So in penetrant testing, when we apply this, we use this technique, this method, inspection method, called dye penetrant, liquid penetrant. We want to use a material called develop. It's the white one. Okay, maybe the last one process. This material has a specific function. Okay, maybe it has two specific functions. One of them is to give contrast. The material is commonly white color, gonna give us a very good contrast against the red dye penetrant. And maybe the main function and the most important function is to draw the remaining penetrant using capillary channels, creating capillary channels, very small. Therefore, it is important to note that this material has excellent hygroscopic properties. In this material, if this material remains on the surface for a longer period than necessary, it will eventually attract humidity from the environment. Of course, this is the electrolyte needed for corrosion to develop. So this is an important fact. It is important to post-clean after this kind of testings, even with ultrasonic testing cold plant. Okay, maybe you are not using the right cold plant because, I don't know, there are many reasons, but you need to clean up after this kind of testings. Some of the reasons that I'm in field for inspectors performing the tests incorrectly are, first of all, because the client or supervisor asks them to leave the piece white to know that it has been inspected and controlled. The second one, due to lack of knowledge, believing they are applying a protective coating paint on the material. Or maybe the third one, simply because they don't care or they are unaware of the effects of this material in the corrosion process. We have a couple of more examples of how corrosion caused by contaminants can damage materials in these specific cases. We have stainless steel parts subjected to contact with arsenic and certain types of acids and exposed to high temperatures. Those pictures are after a proper cleaning process. And of course, as we may know, sometimes contamination by certain materials can lead to corrosion. As it is the case when welding or working with carbon steels along stainless steel. It is possible to contaminate stainless steel with sparks or with residues from carbon steel, which can meet the stainless steel. Therefore, stainless steel requires extra care to prevent such contamination in these areas, okay? A couple of picture more. We have a cracking zone here and here, and crevice, of course. This is after cleaning process. Material were in contact with arsenic and sulfur deposits. And that's it. Well, during my presentation, I would like to invite you, even if you're watching this on YouTube, I would like to invite you to learn more about this event that we are organizing. I'm the chair for this event of AMP, the Association for Material Protection and Performance here in the United States. It is called Corrosion. It is called Coatings for Non-Coatings Inspectors. This is going to be in December, the first week, the 5th and 6th day of December. Just 2 days in the Houston AMP Training Center. And we will have 2 days of talks and practical sessions. We aim to blend the fields of welding as well promote understanding among the parties involved in a process or a project like welding, quality control, quality assurance, of course, coatings, and non-destructive testing. So I hope you'll be there. And that's it. Thank you for your attention. Thank you for share. Thank you for comment or for your like, I don't know. And see you in next opportunity.